Whoops, I didn't turn this on. That's not going to work.
While I'm getting set up, so you should have your exam score. I emailed it over the weekend, I believe. 10 points each. 10 times 10 is 100. And I also sent you via Canvas announcements the solution, so I don't have to go over the solutions, I don't believe, since you could look at it if you wish and compare your solutions with my solutions for the test. Okay. And as soon as I can get this going, I'm going to talk already about the next test. All right. Now, some of you may notice there's some stuff here that doesn't make any sense. Okay, we are over here. I'm already into 10.3, so I'm doing polar coordinates. Okay, this here obviously makes no sense. Okay, so let's make it right now. We're going to have the next exam on November the 10th as of now. It would only be pushed back if I fall behind, but I don't think that's going to happen since I was ahead for a while. Okay, so think of it as we just move everything up. Okay, now on the calendar, my original plan was to have the 5th exam on Tuesday the 15th, and then we immediately have the final exam. But if I can push everything up a day, so this goes up to here, this goes up to here, and so on, then maybe I can have the last exam on Thursday, December the 10th, okay, in which case we would have one day on the 15th to have a question and answer session and give you a whole week between the last test and the final exam, as opposed to, oh, taking the last test on Tuesday, then you immediately have the final exam on Thursday, right? So if possible, I'd like to push everything back over to there. So yes, for now, we're still going to aim for November the 10th for exam 4, okay, which is not that far away, but we're almost there. Yeah, so after this test, there's only, quote unquote, one more test, but it's the longest chapter, as you can see, chapter 11. Okay, so I should be done with 10.3 today, and maybe I can sneak in some of 10.4, and we'll go from there. Okay. All right, so I'm going to get started with polar graphs. So you've got our polar graph paper right here. Okay, I will show you what I have, and as usual, my numbers don't match yours since mine are from the 7th edition, but you're still learning stuff. Okay, so you don't have to tell me, oh, my problem 27 doesn't match your 27. Sometimes it does, sometimes it doesn't. So if it doesn't, that's okay. You're still learning how to do the material. Okay. All right, so I'm going to get started with a lot of polar graphs. So that would be starting with problem 29. Right, so I covered everything I needed to up until that point, I believe. Okay. So I was over here, right? So I already did everything up to 25-ish that I wanted to cover. Okay, and now we'll do these. Right. Here we go. All right, so again, some reminders about the polar graph. I've sent it to you already, in fact, a couple of times, I think. It's from mathbits.com. Okay, and again, I'm going to say you must use this. If you don't use it, I'm not counting your homework or quiz or test for to make it easier for me to grade everybody the same way. Okay. Key ideas. These are 15 degrees apart. Okay, so this is 0 degrees, 1, 2, 3, 4, 5, 6. That's 90 degrees all the way around. There are 14 circles. We'll have to keep that in mind. I don't know why it's 14, but I like this paper. I wish there were 15, but you can always go out to the 15th, or you can pretend there's a 15th. In fact, there are some problems where we're going to pretend there's a 15th circle. Okay, now, you don't actually have to draw the 15th circle unless you want to. Okay, we'll just worry about it when we get to it. Okay. All right, so here we go. I'll get started. And please keep in mind, okay, my numbering may or may not match yours. Sometimes it does, sometimes it doesn't. We'll just play it by ear. Okay, 29. R equals -2 sine theta. All right, so there are some things that you always want to work out, like this analysis that I have here. Okay? So we're graphing R versus theta. Just like X versus Y, Imagine when you first learned, the XY coordinate system and you were graphing that. Now we're doing the R theta system. All right, the first thing you want to do is say to yourself, is there a maximum value for R? Okay, so -2 sine of theta. So is there a maximum value for R? Yes, there is. You know that sine of theta always lies between -1 and 1. Okay, if I multiply that by -2, that means the maximum value for R is 2. Okay, all right, now here's the game we're playing. You already see it here, so I'm kind of giving it away, but pretend you don't know that. The biggest R is 2. Now, sort of like the same idea in X and Y, you want to use as much of the graph as possible so the graph doesn't become too small, but you don't want it to be too weird either. Okay, now, I do have 14 circles, we said. Okay. The maximum R is 2. So one way you could do it, but I don't want you to do it, is to say, okay, the 14th circle is R equals 2. Okay, but if the 14th circle is R equals 2, that means it's 7 circles for R equals 1, and that's too weird, right? We don't like going 1, 2, 3, 4, 5, 6, 7 for one circle. That's just too strange. Okay, so we're willing to give up some of the graph, so to speak. So how can I get as much of the graph as possible, but not having it too weird? Okay, so in this case, I'm going to say R equals 2 is the 10th circle. Okay, so the farthest out I'm going to go is the 10th circle. So I've lost the 11th, 12th, 13th, and 14th. So that's not too bad. Okay, what I definitely don't want you to do, okay, is to just say, okay, this is R equals 1, R equals 2. You're wasting all the rest of the graph. In fact, if you do that, I'll take off points. Okay, if you're trying to cram all the graph into just 2 circles, right? So if you try to do the whole graph and say, okay, this is R equals 1, R equals 2, so your whole graph is crammed just right here, and you're not going to use all the rest of it. That's not the way you want to do it, right? So for this one, what's reasonable is if R equals 2, that's 10 circles. Okay, so I've drawn that here. And then you should analyze what's R equals 1. R equals 1 is the 5th circle, and therefore how much is any one circle? 0.2. So that's very reasonable. Okay, so I highlighted it. Now, do you have to draw this darker circle? You don't have to, but I really advise you to do that. Okay, it just makes it easier to plot the points so you can see what's happening. So we said 1, 2, 3, 4, 5 circle is 1. So I kind of highlighted that to make it easier to count. And then 10 circles is 2. So I drew it all the way around. You can see I didn't do it accurately. I kind of missed, but that's okay. So I'm not going to use circles 11, 12, 13, and 14. Okay, and then I mark off key angles like 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Okay, so going all the way around. Okay, so we're just going to mark off every 45 degrees, essentially, every pi over 4. Okay. So I put the equation again, R equals -2 sine theta, R versus theta. Okay, now, you could, of course, get more accurate. You can decide to go, instead of every 45 degrees, you can go every 30 degrees. Okay, you'd have more points. Okay, it would take you longer, though. Okay, you can do it, but I don't think you have to do it. So we just go every 45 degrees. So R, theta, R is a function of theta. So I just count every 45 degrees, or pi over 4. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay. All right. Now, these values here. Okay. So you plug in the theta and you figure out the R. Okay. I'm going to say, I won't forbid you from doing this, but I'm going to say it's very inefficient to just go one by one. Just go one after the other after the other. If you remember your trig even a little bit, I do something I call divide and conquer. Okay, what's divide and conquer? It's sort of like you take key points, then you keep cutting the interval in half, and then you cut that interval in half, and so on. Okay, so you say, what are you talking about, right? Okay, so let's start off with 0. Yeah, I already showed you this, but pretend you don't know this. Okay, what happens when I plug in 0? Okay, sine of 0 is 0. 0 times -2 is 0. Okay, so 0, 0. I also know that after one revolution, I get the same thing because when I plug in 2 pi, it's the same thing as plugging in 0. So I should also have 0 for 2 pi, right? Excuse me. Okay. All right. Now, instead of going one by one, I would cut the interval in half. Okay. So halfway between 0 and 2 pi is pi. Okay. So pretend you don't have all this, right? That this is all gone. And I go to pi. Just cut it in half. Sine of pi I know is 0. So 0 there also. Okay. So right now I have the angles 0, pi, and 2 pi. Then I'm going to cut those in half. Pi over 2, 3 pi over 2. Okay. I think it's a lot easier to fill things out when you do it that way. Okay, pi over 2. Sine of pi over 2 from trig is 1. 1 times negative 2 is negative 2. Then 3 pi over 2. Sine of 3 pi over 2 is negative 1. Negative 1 times negative 2 is 2. Okay, and I don't know if I have enough pens here, but so now I've got all the in-between ones. I'm trying to cover all the ones we haven't gotten yet. Barely have enough pens there. Okay, so I kept cutting in half. So now I have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now I go to all the in-between ones. Okay, so pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. I already know that the sign of this one, this one, this one, this, it's either going to be radical 2 over 2 or negative radical 2 over 2. Okay, it doesn't change. Okay? I know the sign of 45 degrees, 135 degrees, 225 degrees, 315 degrees, i.e. pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. It's plus or minus radical 2 over 2. Okay, now for this case, since we're going to plot it, I don't want to keep it as radical 2 over 2. Okay, you do want to know radical 2 over 2 is about 0.7. I'll write it. Radical 2 over 2 is about 0.707. You can punch that in the calculator. All right, so pi over 4. Sine of pi over 4 is radical 2 over 2, 0.7. 0.7 times negative 2, negative 1.4. Sine of 3 pi over 4 is also radical 2 over 2, 0.7. 0.7 times negative 2, negative 1.4. Sine of 5 pi over 4, that's quadrant 3, it's negative radical 2 over 2, negative 0.7. So negative 2 times negative 0.7 is 1.4. Sine of 7 pi over 4 is also negative radical 2 over 2, negative 0.7. Negative 2 times negative 0.7, positive 1.4. Okay, so if you do this divide and conquer method, you don't have to plug in everything. Okay, and here's something else I'll show you, which you might like, you might not like it, but I like it. So I'll show you. Okay, I already know these are all plus or minus 1.4, right? 1.4, 1.4. Okay, just cover this up. Okay, if I already know it's going to be either 1.4 or negative 1.4, you can pretty much get it just by looking at the two numbers next to it. Okay, and what do you mean by that? Look at 0 and negative 2, right? If you go from 0 to negative 2, would it be more reasonable to have positive 1.4 or negative 1.4? It makes more sense to have negative 1.4, right? If you think of the number line. Okay. And play that same game over here. I'm going from negative 2 to 0. If I go from negative 2 to 0, which is more reasonable, negative 1.4 or positive 1.4? Negative 1.4. Same thing over here. We don't know these yet. I'm going from 0 to 2. So which seems more reasonable, 1.4 or negative 1.4, positive 1.4? Okay. And likewise, if I go from 2 to 0, which seems more reasonable, 1.4 or negative 1.4, positive 1.4? Okay. All right, so here we go. Here's the graph. 0, 0 is the pole, origin as it were. Okay. Pi over 4 is negative 1.4. Okay, so pi over 4, I'm ready to go this way, right? But I back up 1.4, so I have to go this way. Okay, and how much is 1.4? That's why you want to write this down for me. 0.2 is 1 circle, so 1.4, that would be 7 circles. Okay, so aiming at pi over 4, I walk backwards 1, 2, 3, 4, 5, 6, 7 circles, and I land over here. Keep going. Pi over 2, negative 2. So pi over 2, I'm aiming this way, but I back up to negative 2, so I put a dot over here. 3 pi over 4, again, negative 1.4, the 7th circle backwards. So 3 pi over 4 is over here. But again, I walk backwards, 1, 2, 3, 4, 5, 6, 7. I land over here. And then by the time I reach pi, I'm back at 0, I'm back at the pole. So if I connect these 4 points, I have this so far. Okay. It looks like that's the whole graph. So what's going on? Well, let's keep going. 5 pi over 4, 1.4, positive. Okay, so 5 pi over 4 is over here. I have 1.4, 7th circle. Hey, I already have that point. And likewise, 3 pi over 2, 2. 3 pi over 2 aiming this way, out to r equals 2. I already have that point. And likewise for here and here. So you're just going to retrace the circle all over again. Okay, let's double check. 7 pi over 4, 1.4. 7 pi over 4, 1.4. That's the 7th circle. I already got that point. And then 0, 2 pi. Once again, I'm back at the pole. So I don't see anything different because you've actually traced the circle twice by doing this. Okay, so that's it. That's how you do this kind of problem. All right, so that's a basic introduction to these graphs. I'm going to do many more of these. Okay, so first ask yourself, what's the maximum R for this problem? Okay, in this case, it was 2, 10th circle. Okay, I don't want to use the 14th circle. I'm using the whole graph, but that's too weird to say 14 circles is 2, which means 1 circle is 7. That's very inconvenient to count by 7s. Okay, so we'll say it's more reasonable to go out to 10, and I will just waste a little bit. I'll waste the 10th, the 11th, 12th, 13th, and 14th circle. All right, now that I know that R equals 2, that's the maximum, that's 10 circles. That means R equals 1 is the 5th circle. Then how much is any one circle? 0.2. And then it helps me graph. Okay, and I make a table like this. You might say, well, my table will always be like this. No, it won't. And how will it change? I'll tell you when we get to it. Okay. All right, so that's that one. Okay, next one I'm going to show you is 33. And that does match. I noticed 29 also matches. R equals theta, theta greater than or equal to 0. By the way, if you stop and think about it, R equals theta, those are the two variables in polar coordinates. What would the equivalent be in x and y? Well, y equals x. You know what y equals x looks like. It's a straight line going through the origin with a slope of 1. Okay, but we get a much more interesting graph for r equals theta. All right, so let me just show you the chart first. R equals theta. Okay, so I put the same values, 0 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, and then you just reduce them all. All right, now R is equal to theta, but when you plot the points, you don't want to have it in radians. Okay, so that's where you want to use your calculator. Okay, so just punch all these things in your calculator as necessary. Okay, I've already done it. And round to the nearest tenth, roughly. Well, you should already know pi is like 3.14. I'll call it 3.1. Okay. Now you can punch it in a calculator, but again, yeah, you can kind of do the divide and conquer. If I double that, 6.3, it's actually 6.28, so round it up to 6.3. Okay. And what's halfway between 0 and 3.1? It's 1.55, roughly 1.6. And then I go halfway there and there. So what's half of 1.6? 0.8. And what's midway between these two? About 2.4. Okay. You could punch these all in your calculator, but again, if you kind of divide and conquer, you don't have to. Just say, what's halfway between 3.1 and 6.3? Well, you can average the two, right? Average means add them up and divide by 2. If I add these two, it's 9.4. Divided by 2 is 4.7. And then go halfway here. Halfway between these two, 3.9. How do you get that? Add them up and divide by 2. What's halfway between these two? 5.5. And by the way, you notice that these are 0.8 apart. This is 0.8, 0.8. These are roughly 0.8, but it may not manifest itself because of rounding off. So that looks like 0.7. But anyway, okay, this is what I have. All right, so the maximum R I have is 6.3. Okay, so let's think about it. The maximum R that I have for my graph for one revolution, 6.3. I have 14 circles. So what seems reasonable to call the outermost? Very reasonable to that R equals 7, be the 14th circle, right? I'll be wasting very little of the graph. And 7 goes into 14 very easily. Okay, so I'm going out to 6.3. So R equals 7 is the 14th circle. What does that mean about R equals 1? R equals 1 is the second circle. And therefore, how much is just one circle? 0.5. So each circle is going to be 0.5 now. Okay, so here's what I'm going to do. Since I already know that, and what makes it easier for me to graph is just go 1, 2, 3, 4, 5, 6, 7, right? Yes, it would be easier for me to graph it if I drew the circle. You can draw it or not. You know, it takes some extra work to draw them all. Okay, so R equals 1. I said R equals 7 is the 14th circle. So R equals 1 is the second circle. And each individual circle is 0.5. So 2 circles, 2 circles, 2, 2, 2, 2, 2, 1, 2, 3, 4, 5, 6, 7. And then I just count over. Okay, ignore this for now. I'll get to it later. All right, so pi over 4, 45 degrees, 90 degrees, 135, 180, and so on, right? So we know this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. See what I'm doing? I'm just counting, but I'm reducing the fraction as I go along, right? 1 pi over 4, 2 pi over 4, 3, 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay, so here we go. So pi over 4, 45 degrees, 0.8. Okay, so 0.8. Each circle is 0.5, so it's about 1.5 circles, so I went into that. Okay, pi over 2, 90 degrees, 1.6. 1.6. Each circle is 0.5, so it's a little bit past the third circle. 1, 2, 3, and then a little bit, right? This would be 1.5, so I just put a little bit beyond it. 3 pi over 4, 2.4. Okay, so 1, 2, and a little bit more, so 2.4. You can see if I darken the circles like I did the previous one, right? It'd be a little bit easier, but be that as it may. Pi, 3.1. Okay, so 2 circles is 1, 1, 2, 3, and a little bit beyond. So there we go. Okay, keep going. 5 pi over 4, 3.9. That's almost 4. So I'm going to go out to 4 and just back up a tad. Okay, so where's 4? Remember that r equals 1 is 2 circles. So you're aiming at 5 pi over 4, right? So 1, 2, 3, 4, and then I just back up a tad. So there's roughly 3.9. Okay, then 3 pi over 2, 4.7. Okay, so 2 circles is 1, 1, 2, 3, 4, 4.5. This would be 5, so 4.7 is somewhere in the middle, like that. Okay, 7.7 pi over 4, 5.5. So you aim this away. Again, 2 circles is r equals 1. So where am I going? 5.5. Okay, so 2 circles is 1, 2, 3, 4, 5, 5.5. Right? So it's the 11th circle. And finally, 2 pi, 6.3. All right, well, I can just look at this. This is 6, this is 7, that's 6.5. So roughly over here. Okay, so if I connect it, I get a spiral. Okay, so r equals theta is a spiral shape. Okay, I'll just go ahead and mention that's not the only possible spiral. There are other equations that could come out to be spiral, but this is one possible spiral. Okay, notice a nice thing about this, r equals theta. Remember, if you just set the two variables equal to each other, that's like y equals x in xy coordinate system, okay, which is a straight line, right? Slope of 1 goes up at a 45-degree angle. Yeah, kind of boring, maybe. But when you make it r equals theta, you get your spiral shape. Okay, something else I want to mention, we didn't have to stop here. You could keep going. As the angle keeps going, the arc increases. So this thing will keep spiraling out. It will keep going and back and going farther and farther away. So you do indeed get your spiral shape. Okay. The other thing I want to mention is I'm pretty sure you've never seen this in X and Y. It is not a nice equation in X and Y. You've never seen spirals in X and Y coordinate system. Okay. But in polar coordinates, very nice. Here we are. So this thing actually keeps going out. Okay, I'll just sneak it over here. So if we were to keep going, you would actually see it start to go more and more and more like this, right? So that's the actual spiral. Okay? And you see some spiral shapes in nature. Some animals have shells that are kind of like that. Okay. When you roll paper, like toilet paper or paper towels, it's a spiral, right? It wraps around like so. Okay. The other thing I want to mention is in the original problem, it said theta was greater than or equal to 0. What happens if you have a negative theta? If you have negative theta, you would actually start bouncing the other way. So it would go that way. You get the mirror image. Okay, so this would start spiraling the other direction also. Okay, so that's that. All right, so try to show you everything here. I can't put the whole thing on one screen, so I have to kind of scroll back and forth here for you to see everything. All right. Okay, the next one I'm going to show you is my 35. Just seeing if that's the same thing. Nope, it's not the same. You have 3 cosine 3 theta. I have 4 sine 3 theta. Well, that kind of illustrates the same principle. Okay, so this is not quite the same. Okay, 4 sine 3 theta. All right. First, let's get some fundamentals down. Okay, based on this, what's the maximum value for r? I already showed it to you, but okay, it's a sine function. Sine is between -1 and 1. So the maximum r is 4. All right, I've got 14 circles. So what would seem reasonable? 12th circle, right? And you can see I want all of you to think about this, so that's why I want all of you to have the same polar graph paper. If you have a different R, it'd be different. And besides, I'd have to grade different polar graph paper, and I want everybody to have the same thing. So please use only this graph paper. Okay, so R equals 4, 12 circles. I'm going to waste the 13th and 14th circle. That's not too bad. So what does it make R equals 1? 3 circles. So what about 1 circle, or 1/3, or roughly 0.3? Okay. And you could say 0.33333, but when you plot it, when you graph it, right, you can't even be that accurate. Okay, so as you can see, when I start graphing it, I've got R equals 1 to 4. So this time I decided to draw the circles, 1, 2, 3, and 4. Okay, and by the way, you can see the last time I did this, I messed up. So this squiggly thing here, that's wrong. The actual one is this one here. Okay, so sorry about that. Okay, here's our first instance where, okay, you might say, am I always going to use the same angles? 0, pi over 4, pi over 2, 3, pi over 4. No, we're not. And here's the reason why. Okay, suppose I did the usual thing, pi over 4, right? That same chart. If you plug in pi over 4, you're taking the sine of 3 pi over 4. That's way over here. I'm losing a lot of the graph, right? I'll be losing a whole bunch of the graph. Instead, when I have 3 theta, I'm actually going to have to do 3 times as much work. Sorry about that. That's the way it goes. Okay, so let's say if it's 2 theta, your table is going to be twice as big. 3 theta, 3 times as big. 4 theta, 4 times as big, and so on. Okay, now, how am I going to do that? I'll talk about degrees first, and then come back to radians. Instead of going every 45 degrees, okay, these are 45 degrees, right? 45 degrees. Okay, what's 45 divided by 3? 15 degrees. I'm going to go every 15 degrees. Okay, these marks are every 15 degrees. Because what happens if I plug in 15? What's 3 times 15? 45. I end up with the angles that I want. Okay. The next one will be 30. What's 3 times 30? 90. Pi over 2, and so on. Okay. So instead of this table, I'm going to have to take every 15 degrees, which is pi over 12. Right? And think about it, right? So your table has to be in radians. I don't mind that you temporarily think in degrees, but you must give me the table in radians. Okay, so 15 degrees. You say, I don't do that much in 15 degrees. By the way, very fortunately, these are every 15 degrees. They gave it to us that way. So that's very nice. It's actually less convenient to have 2 theta or 4 theta. Okay, that's going to be a lot worse, actually. But here they give it to me every 15 degrees. Okay, so I need 1/3 of pi over 4. That's going to be pi over 12. Okay, so we chop it like so. So this is pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, 6 pi over 12, and so on. Okay, now I'll show you the table. And I want you to do it this way too. Okay. If you think back to trig, okay, the sine and cosine functions both have a period of 2 pi. If I put a 3 there, that makes it 2 pi over 3. Okay. You should split up your table exactly like this, and there's a reason why. Okay, from 0 to 2 pi over 3. In other words, these numbers kind of match this. I have here what? 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice here 1, 2, 3, 4, 5, 6, 7, 8, 9. So I go out to one period, 2 pi over 3. This next one will go out to 4 pi over 3. The next one will go out to 6 pi over 3, or 2 pi. Next, how do I fill out these numbers? Okay, you start off with your smallest value and just take multiples of it and reduce the fraction whenever possible. So you should be able to show me the reduction of the fraction, but that helps you to count. Okay, that's a lot faster than taking all the angles and saying, oh, I take this multiplied by pi over 180 or 180 over pi. You could do that, but that's way too long. Okay, just come up with your smallest unit. I got pi over 12. Okay, so one more time. On most typical graphs, if there's no number in front, like 2 theta or 3 theta, then we just go every pi over 4. In this case, I want 1/3 of it. So what's 1/3 of pi over 4? Pi over 12. Okay, now watch how I count, but look at the numbers that I put in here. All right, so pi over 12, 2 pi over 12, pi over 6, right? 3 pi over 12. Notice I reduced the fraction, and you should also. 4 pi over 12, 5 pi over 12, 6 pi over 12, that's pi over 2, 7 pi over 12, 8 pi over 12, right? So if you count that way, you don't have to stop and figure out each individual one. And just keep going. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, right? So this was 8 pi over 12, 9 pi over 12, notice the reduction, 3 pi over 4, 10 pi over 12, 5 pi over 6, 11 pi over 12 is just 11 pi over 12, 12 pi over 12, pi, 13 pi over 12, 14 pi over 12 reduces to 7 pi over 6, 15 pi over 12 reduces to 5 pi over 4, 16 pi over 12, 4 pi over 3, 17 pi over 12 is 17 pi over 12. 18 pi over 12 reduces to 3 pi over 2. So as I count, I reduce the fraction as I go along, if you can reduce it. 19 pi over 12 stays. 20 pi over 12 reduces to 5 pi over 3. 21 pi over 12, 7 pi over 4. 22 pi over 12, 11 pi over 6. 23 pi over 12, 24 pi over 12, which is 2 pi. Okay. So there we go. All right, now for this one example that I have here, these were convenient, okay, because they gave me the graph that way. Okay, said this was 45 degrees. The 3 theta made me cut that in 15 degrees. Oh, nice. They give me 15-degree increments, right? So 15 degrees, pi over 12, 2 pi over 12, 3 pi over 12, 4, 5, 6, all the way around, right? Now, the previous problem that I alluded to briefly, but I'll come back to, this gets a lot worse. Okay, now, if you had a 2 theta, 3 theta. 2 theta means I divide this by 2. 45 divided by 2, 22.5 degrees, pi over 8. They don't give me those markings. So let me show you what I would do instead. Okay. So I know you got all these lines here, unfortunately. Okay, so this is 0, 45 degrees. Okay, there are ignore the red if you could temporarily. 1, 2, 3 marks. That means you have to go 1.5 of these. So here's what I did. There's 1 and there's a half. So there's 22.5. Okay, so one more time. To go from 0 to 45 degrees, there's 1, 2, 3 of these, right? So what's half of that? 1.5. So I go 1, there's 2, so I go halfway. So there's 22.5 pi over 8. Same thing I did over here. I just showed you for demonstration purposes one more. Okay, that's 45, that's 90, right? There's 1, 2, 3 of these. So again, if they gave me 2 theta, I would have to go 1.5 of these. And just keep going all the way through. Okay, now you can see if you have different graph paper, it might be more fair or less fair for you to have this. Of course, it's more convenient if you already have that marking there, which would be kind of rare. But again, to make it fair for everybody, everybody must use the same graph paper. Okay, so you have to go 1.5 here. Okay, now what's much harder, and I think there's one, I'm not sure if there's one homework problem that involves that or not. So yeah, your problem 37 has 4 theta. How would I do 4 theta? Okay, so here's 22.5, right? That'd be cutting it in half. If I have 4 theta, that means I cut each of these in half. So I have to go halfway between these. At that stage, I would just eyeball it. Okay, so what I did was just said, okay, what seems to be halfway there? I just eyeballed it and said, there it is. Okay. Likewise here, 22.5, 45. Okay, I just eyeball it and say, okay, what's halfway? Maybe there. Okay. By that stage, you would have pi over 16, I guess. So pi over 16, 2 pi over 16, 3 pi over 16, and so on. Okay, so I think there's only one problem that had a 4 theta. I wanted you to try one, but only one. But you can see how much longer that problem is, right? So again, the original is every 45 degrees. If you have a 2 theta, you cut that in half, 22.5 degrees, pi over 8. If you have a 4 theta, you have to cut that in half. And at that stage, I would just eyeball, okay, here, halfway is there, halfway is there. And you got to do that all the way around the circle, right? I only give you some examples here. So halfway here, right, between these, maybe it's somewhere there, right? And what's halfway here? Eyeball it, maybe there. And just keep going all the way around. And yes, the angles will be pi over 16, 2 pi over 16, 3 pi over 16, 4 pi over 16, and so on. Okay. All right. Now, I'm only going to consider one period for a good reason. Okay. I hope you'll see it's really, really slow if you just go one by one. Okay. Just go from 0 to 2 pi over 3. Okay. What do you get when you plug in 0? Sine of 0 is 0. Because the period from trig would be 2 pi over 3, I get the same answer if I plug in 2 pi over 3. Automatically, that's a 0. Because what's 3 times 2 pi over 3? If you multiply 3 by 2 pi over 3, you're doing the sine of 2 pi, one period, and that's also 0. Again, I highly recommend this divide and conquer. Cut that in half. What's half of 2 pi over 3? Pi over 3. Plug in pi over 3, sine of pi, 0. Okay, cut that in half. Half of pi over 3, pi over 6. 3 pi over 6 is pi over 2. Sine of pi over 2 is 1. 1 times 4 is 4. Pi over 2. I'll be taking the sine of 3 pi over 2. That is 270 degrees. That's like the South Pole, as it were. That's negative 1. Negative 1 times 4, negative 4. And then this one, this one, this one, and this one, they're all going to be radical 2 over 2, plus or minus. Okay. Now, I already said radical 2 over 2 is like 0.707. Okay. If you're not convinced of that, I punch it for you. Square root of 2 divided by 2, 0.707, something like that. Okay. Multiplied by 4, 2.8. So it's either going to be 2.8 or negative 2.8. Okay. You could work it out, but again, just reason it out. Right? Look at this, 0, 4. If you're going from 0 to 4, which seems more reasonable, 2.8 or negative 2.8? 2.8. Okay. I know you're already seeing this, so I've given away the answers. But same thing, I'm going from 4 to 0. Positive or negative 2.8? Positive. Same thing for these. Go from 0 to negative 4, negative 2.8. go from -4 to 0, -2.8. Okay, that's one period. But stop and think about it. If we were to graph this, you know, in the X and Y coordinate system, that would represent one period. Everything else is a repetition. Remember, if you plug in 2 pi over 3, you're taking the sine of 2 pi. So any angle after that, you're just starting to repeat yourself. So I just simply copy all the rest of the numbers. No need to go one by one. So just follow the pattern, right? 2.8, 4, 2.8, 0, -2.8, -4, -2.8, 0. There's another period. Do it again. 2.8, 4, 2.8, 0, -2.8, -4, -2.8, 0. Very fast. Okay. And in case you're wondering, yes, I need to see this chart on everything you do, on any quiz, test, or homework. You should show me this. Okay. There are graphing calculators now that can graph in polar coordinates. You could just push some buttons and then it does the whole thing, and then you don't learn anything. Right? I want you to be able to show me all this stuff. All right, so here we go. 0, 0, pole. Okay, these are every 15 degrees. Okay, so 15 degrees, 2.8. Okay, so I've marked circle 1, 2, 3, and 4, right? So 2.8. Okay, so I'm aiming at 15 degrees. Okay, 1, 2, that's 3, so 2.8 is roughly there. 45 degrees, sorry, 30 degrees, 4. That's my maximum. Okay, pi over 4, 2.8. So 45 degrees, I'm back to 2.8. Then pi over 3, 60 degrees, I come back into the pole. So it looks like I have one loop, like so. Again, I messed up here, sorry, just ignore that. Okay, keep going. 5 pi over 12, -2.8. So I'm supposed to aim this way, but I back up 2.8. 1, 2.8, like this. So I come over here. And then pi over 2, 90 degrees, -4. Okay, so 90 degrees is here, but I back up 1, 2, 3, 4. So my point is over here now. And I keep going. 7 pi over 12, the next 15 degrees, -2.8. So I come over here. I back up 2.8. So 1, 2, that's 3. So -2.8 is roughly there. And then by the time I reach 4 pi over 3, I come back into 0. I come back into the pole. So I have another branch. Okay, keep going. 3 pi over 4, 2.8. So it's supposed to be over here. I messed up the first time I did it. So that's over here. 5 pi over 6, 4. 1, 2, 3, 4. So that should be, whoops, that should be over here. I did it again. It should be over here. Uh, 11 pi over 12, back to 2.8. And by the time I get to pi, I'm back at the pole. Okay, so right now I have 3 branches. So pretty nice. It traces like that. And it comes down over here. And it swings over here and back. Okay, this is sometimes called a 3-leaf rose. Okay, there's like 3 petals to it. Okay, so you have some nice designs. And you notice we never did stuff like this in X and Y. So there's a lot more nice shapes that show up in polar coordinates compared to rectangular coordinates. Okay, as you might guess, you say, well, I'm only halfway through. Well, what happens, just like a previous problem, we just have repetition. 13 pi over 12, -2.8. So you're aiming this way, but you back up 2.8. Hey, I already got that point. And same thing for all the others. 7 pi over 6, which is aiming this way, it's -4. So that backs you up over here. We already got that point. And if you keep going, all of these are just repeated. Okay, so you get all 3 of these loops. by the time you reach pi, okay, from pi to 2 pi, you just see it retrace the same thing all over again. So you have your 3 loops, like so. All right, so there we go. All right, I'll do one more and then maybe we'll break. Okay, my 30 happens to match your 30, so that works perfectly. R equals 1 minus cosine theta. Okay, so what's the maximum value for R? 2. This is between 1 and -1. If you plug in -1, you get 2. Okay. We've already done a maximum R of 2. That's 10 circles. So we've seen this before. R equals 1 is 5 circles. And so 1 circle would be 0.2. Okay, I'll go ahead and say this, but I'm not getting to it yet. We haven't done a maximum R of 3 yet. Okay, so can you guess what I would do for a maximum R of 3? We have 14 circles. Okay, 14 circles, maximum R of 3. Hint, I sort of already alluded to that. They only give you 14. I will go out to 15, right? So if the maximum R is 3, I would go out to the 15th circle. Now you have a choice of drawing the 15th circle. You know, it's not going to be that easy to draw it exactly. I would say don't even bother. If you have to actually go out to that 15th circle, I would just kind of eyeball it and say, okay, it's going to be out there somewhere. Okay, I'll show you one where the maximum R is 3. I'll show you exactly what I do. I'll do that after I finish this one and we take a break. Okay, this one doesn't have a coefficient in front, so we'll just go with it. Okay, so I decided to draw R equals 1, R equals 2. So just the quote unquote normal angles every 45 degrees. Pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. Okay, and I can't show you this at the same time as this, unfortunately, both of these at the same time. So let me rewrite the function. Okay, plug in 0. Cosine of 0 is 1. 1 minus 1 is 0. That means 2 pi is also 0. Again, rather than going 1 by 1, divide and conquer. Cut that in half. Halfway between 0 and 2 pi, pi. Cosine of pi is -1. 1 minus a -1 is 2. Cut those in half. There and there. It's way easier. Okay. Cosine of pi over 2 is 0. 1 minus 0 is 1. Cosine of 3 pi over 2 is also 0. 1. And then all the remaining ones, that one, that one, that one, that one, are going to have something to do with radical 2 over 2, which is 0.7. Okay. So let's see. 1 minus 0.7 is 0.3. 1 plus 0.7, well, is 1.7. Okay. So my only choices are either 0.3 or 1.7. Now you could plug it in and do, you know, radical 2 over 2 and all that. I don't think you have to. Okay. Your only choices are 3 or 1.7. And follow the logic I have again. Okay. You're going from 0 to 1. What's more reasonable, 0.3 or 1.7? 0.3. You're going from 1 to 2. 1.7. The only numbers you can pick are 0.3 and 1.7. Okay, because it's either going to be 1 minus radical 2 over 2, 1 minus 0.3, 1 minus 0.7, 0.3, or 1 plus 0.7, 1.7. Okay, from 2 to 1, 1.7. From 1 to 0, 0.3. And there we go. 0, 0, pole, origin. Pi over 4, 45 degrees, 0.3. Okay, 0.2 is 1 circle, so I go out to 1.5 circles, right? Okay, pi over 2, 90 degrees, R is 1. Put my dot over there. 3 pi over 4, 1.7. Okay, so that's 1.2467. And then pi 2, 1, 2. So right now it loops around like this. Keep going. 5 pi over 4, 1.7. At least this one doesn't have any negatives. That's nice. So I aim at 5 pi over 4. I go 1.7. So that's 1.2467. Roughly there. 3 pi over 2, 1. That's easy. Right over there. 7 pi over 4, 0.3. So 7 pi over 4 is aiming this way. This is 0.2, so 0.3 is here. And then we come back into the pole. Okay, so we have a shape like this. Very nice shape. Okay. And notice again, you never had shapes like this in X and Y. Okay. I'm not holding you responsible for this, but this has a name. It's called a cardioid. Cardio sounds like heart, so it's kind of heart shape. Look at it like that, kind of heart shape. It's called a cardioid. I'm not going to test you on that, but that's what it's called, just so you know it. All right, so it's break time. I'll stop the share. I'm still going to record. It's easier for me that way. Let me check the chat. Okay. Yeah, again, if you missed attendance, please send me an email. Do you start the graph at the origin? Generally, yes, start at the origin. Okay. And let's see. And I think that's pretty much about it. Okay. So I've got 809. So how about 820, 820, 821 roughly? We'll pick up again. All right.
I don't know if you saw the first one, Professor.
I'm sorry, Rashawn?
I don't know if you saw the first one. How will we put R equals theta into the calculator?
Yeah. So for that one, like if you want pi, do you have a pi button on your calculator? If not, then just use 3.14.
Yes.
Oh, okay. So you know how it goes like pi over 4, right? I would literally
Right.
just hit pi divided by 4, right? And what does it come back with?
0.785.
0.785, right. And I rounded it off to 0.8.
Okay.
And then pi over 2, just punch that out. And that's 1.57. I rounded it to 1.6 and so on.
Okay. I see.
Yeah.
I see. Okay. I see what you did. All right. Cool. Thank you.
Okay. All right. Sure. Thanks. Okay. So we'll break until about 8:20, 8:21. Okay, folks, I'm going to continue on, please. So get back to where we were. I don't think there's anything else in the chat that I need to think about. So yeah. Okay. Put away the chat, put that away. Still recording. So back to sharing the screen. Okay, 41 is a little bit different. And that matches what you have in your book. The next one I'm doing, though, is my 39 is not the same as yours, but it has a similar theme to it. Okay, r squared. R squared equals 9 sine of 2 theta. All right, there's a couple of things going on here. Because it's r squared, I have to think in terms of taking the square root, right? So first I say to myself, what's the maximum value of just the right-hand side? The maximum value of the right-hand side is 9, because sine of 2 theta can be as big as 1. Okay, so the right-hand side has a maximum of 9. So what does it say about r? Maximum is 3. And so there we go. The maximum r is 3. I'm going to call that the 15th circle. Okay, we have 14 circles. You can draw that or just wait until you need it. As you can see, it turns out we only need it in a couple of places. Okay, so I didn't think it was worth it. Besides, if I were to draw it, it wouldn't be very, clean. It wouldn't be very nice. So just assume there's a 15th circle there and just put it there when you need it, right? Just kind of eyeball it. Right, so one more time, there's 14 circles. So the 15th circle would represent r equals 3. All right, then what is r equals 1? 5th circle. And therefore, one circle would be 0.2. We've seen that before, but we saw that before with a maximum r of 2. So that's the same as this one, except now the maximum r is 3. Okay, so just pretend it's there. We just plot it if we need it. Okay, now here's something else. This is a recurring theme. So we had 2 theta. So we're used to going every 45 degrees. We have to cut that in half, 22.5 degrees. Because if I plug in 22.5, 2 times that is 45 degrees. Okay. In radians, that would be pi over 8. Okay. So that's again the place where I have to cut that in half. So here's pi over 4. Here's 0. 1, 2, 3 circles. So I go halfway right there. Okay. Same thing here. So from 45 degrees to 90 degrees, 1, 2, 3. I go halfway between this. That's 3 pi over 8. Same thing from here to here. Okay, you count every 3. 1, 2, 3. So 1.5 would be there. Same thing here. 3 pi over 4 pi. 1, 2, 3 of these. So I want 1.5. All the way around. Pi, 5 pi over 4. 1, 2, 3. That's 1.5. From 5 pi over 4 to 3 pi over 2. 1, 2, 3. So halfway there. And finally, from, not finally, a couple more. 3 pi over 2 to 7 pi over 4. 1, 2, 3. So that's about 1.5. And then 7 pi over 4 to 2 pi. 1, 2, 3. So 1.5 would be there. Okay. So there we go. Okay, so how do I make my chart? Again, the period is pi. So I go from 0 to pi, and then I go out to 2 pi. Notice this is just as long as all the other ones. There were 1, 2, 3, 4, 5, 6, 7, 8, 9 entries. 1, 2, 3, 4, 5, 6, 7, 8, 9 entries. Okay, and how do I come up with this? Easy, just count by pi over 8. Okay, so I know this is pi over 4. Half of that is pi over 8. So just count pi over 8. So here we go. Pi over 8. 2 pi over 8. Pi over 4. 3 pi over 8. 4 pi over 8. Pi over 2. 5 pi over 8. 6 pi over 8, 3 pi over 4. 7 pi over 8, 8 pi over 8, pi. 9 pi over 8, 10 pi over 8, 5 pi over 4. 11 pi over 8, 12 pi over 8, 3 pi over 2. 13 pi over 8, 14 pi over 8, 7 pi over 4. 15 pi over 8, 16 pi over 8. Okay, now look at how I made this chart. Because they said r squared equals blah, 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 my chart's going to be like so. First, I plot r squared versus theta, because that's how they give it to me. Okay, it's much, much easier to do that way. So notice I have r squared theta, r squared theta. Okay, so first I figure out r squared. I mean, once I have the r squared, I know how to find r. Just take the square root, right? So think in terms of plotting r squared versus theta, and then after that, I figure out the r. Okay, plug in 0. Sine of 0 is 0. 9 times 0 is 0. That means 1 period pi would also be 0. Notice if I plug in pi, I'm taking the sine of 2 pi, which is 0. Cut that in half. Halfway between 0 and pi over 2. Plug in pi over 2, I'm taking the sine of pi, which is again 0. Cut those in half. Pi over 4, 3 pi over 4. If I plug in pi over 4, I'm taking the sine of pi over 2. That's 1. 9. If I plug in 3 pi over 4, I'm taking the sine of 3 pi over 2. That's negative 1. Negative 1 times 9 is negative 9. And then all the rest have something to do with radical 2 over 2. If I plug in pi over 8, I'm taking the sine of pi over 4. That's radical 2 over 2, 0.707, something like that. Multiplied by 9, 6.4. So I'm either going to have 6.4 or negative 6.4. Okay, I know you've already seen it, but just reason it out. 0, 9, 6.4. 9, 0, 6.4. 0, negative 9, negative 6.4. Negative 9 to 0, negative 6.4. See, this is way faster, in my opinion, way faster than going one by one. Figure that out, figure that out. No, if you do this cutting in half business, much, much faster. That's 1 period, which means copy and paste. So 6.4, 9, 6.4, 0, negative 6.4, negative 9, negative 6.4, 0. Okay, this is r squared. Now let me do the r's. Okay, square root. Well, what's the square root of 0? 0. 0, 0, 0. R squared is a negative number. R squared is a negative number, can't do it. So no graph, no graph, no graph. It's not in the domain. That's okay. In X and Y, we had graphs that had limited domain. So in polar graphs, you can have a limited domain also. And now 9, this gets a little tricky. Technically, you're doing r squared equals 9. You have to have a plus or minus. So plus or minus 3. Plus or minus 2.5, roughly. And nothing, nothing, nothing. And just copy over here. So these match because these match. So plus or minus 2.5, plus or minus 3, plus or minus 2.5, nothing, undefined, 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 0. Okay, so it's almost like the graph sleeps. The graph doesn't exist for a while. It goes to sleep after pi over 2 and then wakes up again at pi, so to speak. Okay. So here we go. Now, when you graph it, you have to ignore the r squared. Okay, you're graphing r versus theta. Okay, 0, 0, we got that. Okay, pi over 8. That's 22.5 degrees. Okay. Notice it's plus or minus 2.5. Okay. 1, 2.5, 1, 2.5. Okay. Pi over 4 plus or minus 3. That's the 15th circle that I was talking about. Okay. So again, I don't think it's worth drawing the circle. Every 5 is 1, right? So 1, 2, 1, 2, 3, 4, and I just eyeball it. Okay, there's 5. That's the 15th circle, quote unquote. And since it's plus or minus, I also have to go back. 1, whoops, over here. 1, 2, that's the 14th circle. So there's my pretend 15th circle. Okay, keep going. 3 pi over 8 plus or minus 2.5 again. Okay, so 3 pi over 8 is over here. 1, 2.5, and negative 1, 2.5. And then by the time I reach pi over 2, 90 degrees, it comes back into the pole on both sides. Okay, so it's like this right now, and I also have a branch like that. And then it's almost like the graph stops. It just goes to sleep between pi over 2 and pi. So that's why there's no graph over here. So you keep going, 5 pi over 8, undefined, 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 undefined. It goes to sleep, and then it wakes back up at pi. So pi is 0. Okay, 9 pi over 8 plus or minus 2.5. We already got it. So again, we're just duplicating ourselves. So that is there, that is there. 5 pi over 4 plus or minus 3. We already got that. 1, 2, 3, positive. 1, 2, 3, negative. 11 pi over 8, 2.5. Here's 11 pi over 8. Positive 2.5, negative 2.5. 3 pi over 2 comes back into the pole. And then again, it falls asleep between 3 pi over 2 and 2 pi. So nothing, 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 until we finally get back to 2 pi, and then it just traces all over again. Okay, so you have this shape, almost looks like a figure 8, okay, or sideways infinity symbol. And again, notice we never had a graph like this in X and Y, so it's pretty neat, the kind of graphs that you can have in polar coordinates that we never saw in rectangular coordinates. Okay. All right, and one more that I want to show you of this type before I move on. Okay, by the way, that's not all there is to this section. After the graphs, we have some slope of the tangent lines to discuss over here, right? So that would be the end here, I guess that would be 55 to 63, something like that. Okay, my 39 is r equals 1 minus 2 sine theta. Okay, the one here is 1 plus 3 cosine theta. Okay, so it's kind of the same thing. This one has a maximum value of 4. We've already tackled that before. Okay, that would be the 12th circle, I believe, right? Okay, mine is r equals 1 minus 2 sine theta. Okay, but similar theme. Okay, this has something different that I need to show you. Okay, so what's the maximum value of r? 3. If you had 1 minus a minus 2, right? That's 3. So again, 15th circle, and it shows up, it doesn't show up until over here, I guess. So yeah, I don't think it's worth it to draw the 15th circle. Just put the dot out there, guesstimate it when you have to use it. There's no coefficient in front, so very fortunately, I just have to do my normal 45 degrees, right? And just like the previous one, r equals 1 is the 5th circle, and r equals 0.2 is 1 circle. It's equals 0.2. Okay, so I just have my usual number, so to speak, from 0 to 2 pi. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, right? Okay. Okay, plug in 0, sine of 0, 0, 1. Again, I don't recommend going one by one. It's a lot easier just jump straight to the end. 2 pi, 1, right? You already know these are going to match. Divide and conquer pi. Cut that in half. Sine of pi is also 0, so again 1. Cut those in half, pi over 2, 3 pi over 2. Sine of pi over 2 is 1. 1 minus 2 is negative 1. Halfway here would be 3 pi over 2. Sine of 3 pi over 2 is negative 1. Negative 2 times negative 1 is a positive 2. 1 plus 2 is 3. So that's where my maximum, my 15th circle is, right? So you can kind of see it only happens at one dot. So we're going to have that one dot. You know, it's not really worth it to try to draw that 15th circle. If I were to draw it, it wouldn't be very accurate anyway. We only need it at one spot, so just there. Okay, now what about all the other ones? Okay, something to do with radical 2 over 2, 0.7, right? 0.7 times 2 is 1.4. So it's either going to be 1 minus 1.4, negative 0.4, or 1 plus 1.4, 2.4. Okay, so again, this is either going to be plus or minus 1.4, 1 minus 1.4, negative 0.4, 1 plus 1.4, 2.4. So I'll just go by what's reasonable. I'm going from 1 to negative 1, negative 0.4. From negative 1 to 1, negative 0.4. From 1 to 3, 2.4. From 3 to 1, 2.4. Okay, now here's something that's a little bit different. We haven't done this in any of the previous ones. There is no 0 on the table here, but you know there is going to be a 0. How do I know? Well, you pass from 1 to negative 0.4, so it's got to be something in here, right? And likewise, you pass from negative 0.4 to 1. It does it in a continuous fraction, okay? So there's no jumps. So if you're going to go from negative 0.4 to 1, it's continuous. You have to pass through 0. Okay? So it's worth it to find out where does it come into 0. That tells me where it's going to come into the pole. And you can see it does come into the pole. Okay, so we have to take a little extra step and fill in a little bit more of the chart, so to speak. Solve 1 minus 2 sine theta is equal to 0. Okay, so one more time. We know there's a 0. It doesn't show up in our chart. It did show up in our previous charts, but it doesn't show up here. But you know it's there because you jump from 1 to negative 0.4 and also from negative 0.4 to 1. So it is worth it to find out where does it come into the pole. So 0 equals 1 minus 2 sine theta. A little bit of algebra. Sine of theta is a half. Y coordinate is a half. That's here and here. So at pi over 6 and 5 pi over 6. Okay, so at 30 degrees, it comes into the pole. You can imagine that you're sneaking it in here somewhere. And at 5 pi over 6, it also comes in to the pole. Okay, so I'd keep that in mind. All right, so here's my chart. So theta is 0, r is 1. So 0, here's 1. Okay. 45 degrees, pi over 4, negative 0.4. So I'm aiming at 45 degrees. I walk back 2 circles. Okay. And I know it comes into the pole at pi over 6, 30 degrees. So 30 degrees is here. So I wrote in pi over 6 specially. So when I reach 30 degrees, it comes into the pole, and then it continues on over here. Then we get some more negatives, it looks like. Okay, so where are we? Pi over 2, negative 1. So 90 degrees, you back up 1. And so you can see the advantage of drawing these sharper circles. I can tell right away this is negative 1 or 1. Okay. Then 3 pi over 4, back at negative 0.4. So you're aiming here, but you back up 0.4, which is 2 circles. So there. And again, by the time I reach the pi, I'm out at 1. That's over here, but you do have to pass through 0. That's once again, we had to find out at 5 pi over 6, it comes into the pole again. So 5 pi over 6 is here. So as I come into 5 pi over 6, I reach the pole, and then I come back out after that. And it looks like we have no more poles after that. There's no more zeros. After that, it's all positive. So we just do the normal after that. Okay, so the rest is pretty straightforward. 5 pi over 4, 2.4. So 1, 2, 2.2, 2.4. 3 pi over 2, 3. All right, so that's that one place where I go out to the imaginary 15th circle. So 1, 2, right, 2.2, 2.4, 2.6, 2.8, 3. So again, you can see it's just one dot. It's not really worth it to draw the whole circle. So there it is. 7 pi over 4, 2.4, 1, 2, 2.2, 2.4. Again, 0.2 represents one circle. So I'm there. And then I come back into 1 at 2 pi. So 2 pi and back to 1. So I have this funny shape. Okay. So there's an inner loop and an outer loop, as you can see. All right. Okay, so that's polar graphs. We've already used up a whole bunch of our polar graph paper. In case you're worried about running out, this is the majority of the graphs that we have. We will have few and far between from here on out. Okay, maybe a quiz and the exam and maybe final exam, right? And there's a few more that you might have for the next section, but this is by and large the majority of it. Okay. All right, so that's that. I'm leaning toward for Thursday's quiz to have you do one of these things. Okay, so at the end of Thursday's class, I'll give you one of these polar graphs. You'll use up another one of these and the usual stuff at the end of class. I'll break you into your breakout rooms and it's due the following Tuesday. So there we are. Okay. All right, so that's that. Now, believe it or not, we're actually not done with the section. So what's happening here now? 55 to 63. Find the slope of the tangent line to the given polar graph at the point specified by the value of theta. Okay, so we have these polar graphs, right? Look like that, or whatever. We still want to be able to talk about what's the slope of the tangent line. And when we say the slope of the tangent line, it's the normal dy dx, not dr d theta necessarily. Okay, what's the rate of change of y with respect to x? What's the slope here? What's the slope here? What's the slope here? And so on. Okay. So, more formulas. Tangents to polar curves. Okay. Now, we have x equals r cosine theta, y equals r sine theta. Think of r as f of theta. Okay. You could do the product rule and the chain rule, and you can find dy d theta and dx d theta. I won't go over that, but it's basically the product rule and the chain rule. Okay, so dy dx is dy d theta divided by dx d theta. Again, that seems reasonable, right? If you kind of pretend that you cancel out the d thetas, right? If you kind of cover up the d thetas, it says dy dx. And I'll divide top and bottom by d theta. Okay, so dy d theta, you would use the product rule. It looks like that. Dx d theta looks like that. Okay, so here's the formula. And they didn't box this out. I don't know why, but here we are. Go ahead and put this on your cheat sheet. Where is it? It's on page 663. So don't memorize it. But here we go. So notice this is the normal dy dx, rate of change of y with respect to x. Okay. Some things to notice. R is a function of theta. You're going to plug that in. Okay, so like what did we do? We had r equals 1 plus cosine theta, or r equals sine of 3 theta, or something like that. That gets plugged in right over here. Okay, that stays the same as that. That stays the same as that. That's always going to be there. Okay, so the things that we have to compute are just dr d theta. Okay, that's pretty easy. And what's the original r? Okay, and I'll show you how to do that. Okay, then the other thing that happens is they'll talk about horizontal and vertical tangents again, right? So same thing, horizontal tangent means it equals 0. The numerator is 0. Vertical tangent, denominator is 0. Okay, so that's what's happening there. All right, so I'll show you how to do that, and then that's going to be it for 10.3. Let's see what time is it. I can maybe sneak in a little bit of 10.4, but not much. Okay, so find the slope of the tangent line. Okay, find the points of the graph where the tangent line is either horizontal or vertical. Okay, so I'll do a couple of these and maybe one of these, and that's about it. Okay, and again, it's my version, which may not match your version. We shall see. All right, so I wrote the formula again here. Put this on your cheat sheet. dy dx, dr d theta sine theta plus r cosine theta. Dr d theta, that's not that hard. You just take the derivative of this. Okay, divided by dr d theta cosine theta minus r sine theta. Okay, r is this thing that gets plugged in. Okay, and then you just plug in whatever. Okay, so my 55, let's see, it does not match your 55. You've got r equals 2 cosine theta. Oh, well, if r equals 2 sine theta, be that as it may. It's all right. It's the same principle. Okay, now here's the way it works. What is dr d theta? Look at this. 2 cosine theta, right? Dr d theta. That goes here and here. So notice I just copied the same thing there. 2 cosine theta, 2 cosine theta, right? Dr d theta by formula. This r and this r are just the original function. 2 sine theta. There's r. 2 sine theta, 2 sine theta. And then in the formula, it's always sine, cosine, cosine, sine. So there it is. Sine, cosine, cosine, sine. So it's not really that bad. Okay, it looks like a scary formula, but you're not memorizing it. Okay, so you do have to figure out dr d theta. You put the same thing here and here. The original function, r, 2 sine theta, goes here and here. And then it's always sine theta here, cosine theta here, cosine theta here, sine theta here. Okay, so clean it up. This is 2 cosine theta, sine theta. Here's another 2 cosine theta, sine theta. So that's a grand total of 4 cosine theta, sine theta. And the bottom I have 2 cosine squared theta minus 2 sine squared theta, which I can factor this out. So I can cancel right here. So 2 sine theta, cosine theta divided by cosine squared theta, sine squared theta. Okay, I did some extra stuff here just for fun. You could actually make it much nicer. That happens to be the formula for the sine of 2 theta. This happens to be the formula for the cosine of 2 theta. So the easiest way to write the derivative is tangent 2 theta, although that's actually not going to be that easy to plug in. The easiest to plug in is this one here. Okay, so I wrote for you again if you need it. Sine of 2 theta is 2 sine theta cosine theta. Cosine of 2 theta is cosine squared theta minus sine squared theta. So this is the nicest way to put it, but in terms of computing, it's probably easier to do this. So I'll plug in here. So they told me to plug in pi over 6. So if I double pi over 6, I have pi over 3. So sine of pi over 3 divided by cosine pi over 3. Okay, pi over 3 is 60 degrees. So draw myself a unit circle, 60 degrees. Either x or y is going to be 1/2. So if I look over here and look over here, it looks like x is halfway across the circle, right? From there to there, that's halfway. That's more than halfway. So that means x is a half, y is automatically the other number. The other number is always radical 3 over 2. Okay, sine y coordinate, radical 3 over 2. Cosine x coordinate, 1/2. Okay, and there's a trick that you can just cancel these 2's. So radical 3. So the answer is radical 3. Okay, 57. My 57 does match your 57. R equals 1 over theta at theta equals pi. Okay. Okay, to differentiate this, write it as theta to the -1. That's way better than doing the quotient rule. Right, quotient rule is probably one of our least favorite because, you know, there's more stuff to it. I'd rather do that. Okay, so dr d theta is negative theta to the -2, or negative 1 over theta squared. All right. Plug into this formula. So negative 1 over theta squared goes here and here and here. And R goes here. The original R was 1 over theta. So 1 over theta, 1 over theta. Okay, and then by formula, it's always sine, cosine, cosine, sine. Okay, don't memorize it. Sine, cosine, cosine, sine. Okay, I am plugging in pi. Okay, the sine of pi is 0. That's why I cross that out, cross that out. Cosine of pi is negative 1. Okay, so I have 1 over pi times negative 1 divided by negative 1 over pi squared times negative 1. Well, the two negatives become positive. Okay. And if I multiply top and bottom by pi squared to clean it up, I got a negative answer. Pi squared times 1 over pi is pi. Pi squared times 1 over pi squared is 1. So my answer is negative pi. So there we go. All right, then I'll do 61 and then I'm done. It's almost 9 o'clock. I'll be finished in the next few minutes. So introduce some of the next section, 10.4, just to save time next time. Find the points where the graph is horizontal or vertical. Okay, so R equals 3 cosine theta. Let me go ahead and work that one out and see what happens. So here's something else that we will learn that's kind of instructive. Okay, but before I go on, recall that we said in polar coordinates, there's often more than one way to label a point, right? So if you have, let's say this was 1 comma 0, I could say 1 comma 2 pi. Or I could say negative 1 comma pi, right? Now in X and Y, there's only one way to label a point X and Y, right? How much do you go X? How much do you go Y? But there's lots of ways to label a point with R theta. Okay, so keep that in mind as we do this problem. Okay, so first I figure out dy dx. Here's the formula. Fortunately, you can see both on the same screen, I think. So dr d theta, what's the derivative of 3 cosine theta? Negative 3 sine theta, dr d theta. So that gets same thing here and here. The original R, 3 cosine theta here and here. Plus, minus by formula. And it's always sine theta, cosine theta, cosine theta, sine theta. So here's dy dx. All right, so I factored out the 3, and I put cosine squared theta minus sine squared theta. Here you have negative 3 sine theta cosine theta minus 3 cosine theta sine theta. Well, that's the same thing. So the bottom is negative 6 sine theta cosine theta. Clean it up. I factored out the negative. So negative cosine squared minus sine squared divided by 2 sine theta cosine theta. Okay. All right. Horizontal tangent, numerator is 0, right? So cosine squared minus sine squared equals 0. Cosine squared equals sine squared. Sine theta is plus or minus cosine theta. Okay, so the sine and cosine are either the same or the opposites here, 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 here. So I have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay. Then I plug in. Okay, cosine of pi over 4, radical 2 over 2. Multiplied by 3, 3 radical 2 over 2. Okay, and you have to be careful. It's R is a function of theta, but it's always written R theta. So you might be tempted to put pi over 4 comma 3 radical 2 over 2. Okay, but it's always R and then theta, not theta and then R. So 3 radical 2 over 2, pi over 4. 3 pi over 4, cosine is negative. So if you can get through that, negative 3 radical 2 over 2, comma 3 pi over 4. Ignore the red for the time being. 5 pi over 4, 5 pi over 4, cosine is negative. So negative 3 radical 2 over 2. Remember, it's supposed to be negative radical 2 over 2, but we're multiplying by 3. So negative 3 radical 2 over 2. And then 7 pi over 4, cosine is positive. 3 radical 2 over 2, 7 pi over 4. Okay, now what's all this crossing off stuff? Okay, superficially at the beginning, it looks like 1, 2, 3, 4 points, but it really isn't. And here's why. 3 radical 2 over 2, pi over 4, negative 3 radical 2 over 2, 5 pi over 4. These represent the same point. They are 180 degrees apart, pi radians, right? Pi over 4, 5 pi over 4. This one is positive 3 radical 2 over 2. This one, you're aiming 180 degrees apart, right? So you're ready to aim this way, negative 3 radical 2 over 2. So you back up, so you end up at the same spot. And the same thing happens here. 3 radical 2 over 2, 7 pi over 4. Okay, that's over here. Where is 3 pi over 4? 3 pi over 4 is over here. Negative 3 radical 2 over 2. So you back up the same amount. So again, you have the same point. Okay. So the convention is you don't leave 4 points. If it names the same thing, you cross off any duplications. Okay, they represent the same thing. So what's the convention? Can you see why I crossed these two out and left these? R is negative, right? We like positive. Okay, so I established these two are really the same point. Which one do I keep? How about I'll keep the positive R? Makes sense. Likewise, that is the same point as that. I'll keep the positive. Okay, that's what you should do, by the way. So I will only present my answer as 3 radical 2 over 2, pi over 4, 3 radical 2 over 2, 7 pi over 4. You don't list these. Okay, and by the way, technically, this is considered wrong because it looks like you have 4 points, but it's not really 4 points. It's only 2 distinct points. Again, please notice you never had this problem in X and Y, right? Because in X and Y, you had the point like 3 comma 10, right? You can't name anything else, right? 3, 10 means 3 to the right, 10 up. There's no other way you can name it. But because in polar coordinates, there's more than one way to label the point, you run into this problem. Okay, so if there's any duplicates, you throw them out. How do you know if they're duplicates? Well, look for the R's being opposites of each other, right? Like positive 3 radical 2 over 2, negative 3 radical 2 over 2. So that, okay, I suspect they might be the same point. And yes, indeed, from the angles are 180 degrees apart or pi radians. So these two are indeed the same point. And likewise here. Okay. Same thing happens for a vertical tangent. So make the denominator equal to 0. So 2 sine theta cosine theta equals 0. That means sine of theta equals 0 or cosine theta equals 0, i.e. x or y is equal to 0. Well, these are the 4 quadrantal angles. 0, 90 degrees, 180, 270, right? Okay, so 0. Okay, remember we're plugging back into 3 cosine theta. If I plug in 0, cosine of 0 is 1, 3. Pi over 2. Cosine of pi over 2 is 0. 0 times 3 is 0. 0 comma pi over 2. Pi. Cosine of pi is negative 1. Negative 1 times 3 is negative 3. So negative 3 comma pi. And plug in 3 pi over 2. Cosine of 3 pi over 2 is 0. 0 times 3 is 0. Okay, so again, superficially, I have 1, 2, 3, 4 points. But once again, look at these two. 3, 0. 0 degrees or 0 radians is here. You walk out 3 units. Here you aim at pi, so you're aiming this way. You back up 3. So those are the same. So 3, 0, and negative 3 pi are the same polar coordinates. Which one do I throw out? The negative r. So I keep 3, 0. And these are the same. They both have an r of 0. So these are the same. Normally, if r is 0, you don't write it. You say the pole. Okay. In fact, think about the coordinates for the pole. R is 0. If r is 0, the angle can be anything you want. The pole, you could say 0, 0, but it's 0, comma theta in general. And we're going to need that theme a little bit later. The pole is 0, 0, but it's also 0, 90 degrees, 0, 180 degrees, 0, 45 degrees, 0, 23 pi over 16. It doesn't matter because if you give me any angle, right? Once you give me the angle, all you're doing is spinning around. Okay. And you say, okay, how far do I walk out? Well, you don't walk out anything. So the pole is 0, comma any angle that you want, right? Because if you stop and think about it, right? You spin this around, you go to any angle, and say, okay, I'm ready to walk out. Now, how far do I walk out? Well, I walk out 0. So the pole is 0, comma theta. So the best way to write this answer is 3, 0, and the pole. So if you get an answer like that, you just simply say the pole. All right. So that's it. Okay, so I'm now done with 10.3. I'll sneak in a little bit of 10.4. It's already 9:05, so I won't go that long. Let's compare that with our calendar. So it looks like I'm a day ahead. I was originally supposed to start 10.4 on next Tuesday, but I guess we can start it here. So I'm a little bit ahead. I'll go on ahead and just give you some introduction, and then we'll call it a day, okay? So 10.4. Areas in polar coordinates. You can also do lengths. I don't think I'm doing any lengths. I'm going to skip the length. Okay, so suppose I go from two different thetas. Okay, now in x and y, we went between two x's normally, right? So you go like x equals -5 to x equals 10, and you have a function. What's the area under the curve? Okay, so this is the equivalent in polar coordinates. Okay, theta equals a, theta equals b. So maybe this is pi over 6, this is pi over 3. Here's r equals f of theta. What is the area, quote unquote, under the curve between two angles? So notice the way it's working, you're going from one angle to another angle, you're sweeping out like so. Okay, so our slices are going to be d theta. Okay, so that's different than x and y coordinates, right? So you might recall in x and y, we did something like this, right? And we swept out for a delta x, right? This was delta x, here's f of x, and then we added up a whole bunch of rectangles, right? Here, we're going to do a delta theta. So delta theta means you're going from one angle to another angle, and you're sweeping it across this way, right? So instead of delta x, we're doing delta theta. So a typical slice is going to look like this. So look at how we chop it up. That's like chopping up with our rectangles. We were going like that, and like that, and like that, and like that, right? We said a whole bunch of rectangles or approximate rectangles. Well, here, look at how the slice is. It's like this. This is a delta theta, a tiny change in angle. Here's a typical slice. Okay. That slice is a sector of a circle. You see, it doesn't look like a sector. Yeah, but if I slice it very, very thin, it looks more and more like a sector of a circle. Technically, this is a sector of a circle. Okay, you start at the radius, draw two radii. It's like a piece of pie. Okay, and if theta is very, very thin, it looks more and more like this. Okay, now the formula for the area of a sector is 1/2 r squared theta. Okay, you may have seen that before. You're going to put this on your next cheat sheet anyway. So a typical slice, a delta A, little change in area, is 1/2 r squared, or they call it f of theta squared, delta theta. It's kind of hard to say delta theta, tiny change in theta. Okay. And then you add them all up. So you're adding up all these sectors. You add up this one, this one, this one, this one, this one, this one. Okay. Over here, we're adding up areas of rectangles. Okay. You said that wasn't a rectangle. Yeah, but if delta x is really, 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 really small, the approximation gets better and better and better as long as you have a continuous function. Okay. So as long as you have a continuous function, if delta theta is very small and you chop slices, they're like this, each of these looks more and more like one of these. And this says you basically add them all up. When you add them all up, you're integrating. Okay, so what are you integrating? It's 1/2 r squared. In the limit, delta theta becomes d theta. Okay, all of that to say this. Okay, now you may have just said, I have absolutely no idea what you were talking about when you did that. That's okay. If you didn't get it, all you need to do is use this formula. Okay, so here we go. Put this on your next cheat sheet. Okay, if you want the area going from two different angles now, the picture is like this, from one theta to another theta in polar coordinates. So this is polar coordinates. In rectangular coordinates, that's like going, x is going from A to B. Chop, 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 delta x, rectangles. Here, chop, 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 delta theta, the slices look like this. Okay, and we're adding up a whole bunch of 1/2 r squared delta thetas. Okay, bottom line, use this formula. Okay, so what's going to happen is we're going to find the area going from one angle to another angle, and here's the formula, 1/2 r squared d theta. Okay, r is f of theta. You just basically replace r by what the formula is. And yes, you can always factor the 1/2 out. Okay, so I'll just mention this very quickly, and then I'll be done, unless anybody has a question. Okay, so let's pretend you know we're going from -π/4 to π/4. Okay, so integrate from -π/4 to π/4. Here's the area and region. We might want to know what's the area of this, right? So the function is r equals cosine of 2 theta. So from -π/4 to π/4, there it is, -π/4, π/4, 1/2 of r squared d theta. So I just square that, cosine squared 2 theta. The 1/2 comes outside. And yes, notice that trick that we've seen before. If you look at this, you say, oh, by symmetry, I get the same area here as here. So rather than going from -π/4 to π/4, I'll just go from 0 to π/4 and double it. That's nice because I like plugging in 0. And not only that, notice if you double, you get to cancel that half. It's 1/2 times 2, 1, and then you just integrate from 0 to π/4. So that's the best of both worlds. Not only do you get rid of that half, but you get to plug in the 0. Okay, then the rest you just integrate. Right, so that's essentially it. Okay, so I wasn't going to do any problems now, but you can see where we're headed. Okay, find the area of the region that lies between blah, 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 blah. Okay, so notice we're between two angles, between 90 degrees and 180 degrees, π/2 and pi. Here's the function. Okay, so whatever it looks like, okay, we're integrating between two angles. What's the area of the specified sector? Okay, and the formula you're going to use is this. All right. Okay, so I'll save that for next time. I'm done, folks. So let me stop the share. Check the chat. What time is it? 9:10. Okay, that's it. So if anybody has a question now, you can either unmute yourself or you can put it in the chat, but otherwise we can call it an evening and then we're done. So most likely on Thursday, I'll stop early and you'll be doing one of these polar graphs, right? One of the graphs that we just did today, you know, stuff like this or whatever. Okay, anybody want to ask me anything, please? Okay, hearing nothing, then we will adjourn for tonight. Okay, so that's it, folks. Have a good night. I'll start the next section next time and be ready for the quiz next time. All right, good night, everybody. Bye.